Alright, this screencast is going to be about properties of acids and bases. Okay, and the first thing we're going to look at is neutralization reactions. Neutralization reactions. And we can look at this as double replacement, and what will first react is nitric acid and sodium hydroxide. Okay, and in the reaction of an acid and base, you'll get water and a salt, in this case sodium nitrate, and that's in its solution. Okay, now this is what you would call a molecular equation. Wow. Wait a minute. Okay, so having trouble. Molecular equation. What would it look like if we make it into an ionic equation? Remember, for an ionic equation, what we're going to do is take anything that is soluble in water and show it how it exists in solution. So we would have the hydronium ion, the nitrate ion, the sodium ion, and the hydroxide ion, all in solution, making water, which is kept together because it's a covalent compound. And we'd have our sodium ion and our nitrate ion. I did not include the aqueous symbols because I don't have that much room. Okay, so if you notice, I have sodium on both sides. Okay, so we'll be crossing those out to make our net ionic equation, which is where I was going with this. Net ionic, okay. There, if they show up as the same ions on both sides, they're called spectator ions. So your net reaction for the reaction of a strong acid with a strong base, and remember, a strong acid is one that completely ionizes, strong base is one that completely dissociates. We will have the reaction of the hydronium ion and hydroxide making water. Alright, the change in enthalpy for this reaction is a negative, so it's always exothermic, kilojoules per mole. So negative 57.3 kilojoules per mole. Okay, and this is going to be true for any strong acid and strong base. Okay, so basically neutralization reactions can be assumed to be exothermic. Okay, if I had something like a weak acid and a strong base, something like HF plus your sodium hydroxide, I would still get water, and I would get the soluble salt NaF. Looking at the ionic equation, HF, since it is a weak acid, we do not break that apart. Sodium hydroxide is a strong base, so we do break that apart, making water covalent, stays together, plus sodium, sodium fluoride being an ionic soluble, we would break that apart. So our only true spectator in this is our sodium ion. So our net ionic for this equation will be HF reacting with the hydroxide group, forming water, and our fluoride ion. Okay, another type of reaction, we're talking about acids and bases. Remember that a base really can be anything that's going to neutralize an acid. So if we have something like copper oxide, solid, reacting with sulfuric acid, reacting to form copper sulfate and water, this would be considered a base. Another type of reaction to keep in mind is reactions with carbonates or hydrogen carbonates. Okay. Hopefully that you remember that when I react carbonates, such as calcium carbonate, with acids, such as the strong acid hydrochloric, I am going to get calcium chloride, which in this case is soluble, plus H2CO3 carbonic acid. Need to remember that that carbonic acid further decomposes into water and CO2 gas. Next type of reaction is the reaction of metals, or the reaction of, metals with hydrogen in single replacement reactions. Remember this, you have to look at the activity series to determine whether the reaction will actually go or not. Okay, so in the case of magnesium plus hydrochloric solution goes to magnesium chloride, which is aqueous, and hydrogen gas. And that would be the single replacement reaction. Okay, type that we didn't spend a whole lot of time with is reactions, okay, with indicators. Okay, most will just indicate whether the reaction is acidic or basic. So most indicators will just indicate whether solution is acidic or basic. Okay, we have used the universal indicator, which is actually a mixture of several indicators. And this gives us a little bit better of an idea of what the actual pH is. Okay, so what this does is it produces, that universal indicator produces a wide range of colors that are proportional or relate better to the hydronium concentration. Continuing on indicators, for specific indicators, they will change color depending on if it's an acidic environment or a basic environment. Things like litmus. Acidic is red, base is blue. For phenolphthalein, in the acidic it is colorless, in basic it is pink. And we did use that when we did titrations in class. Methyl orange is red as a acid in an acidic environment and yellow in a basic environment. Okay, let's continue this and we'll talk about bases and then move into pH. So, talking about bases. Okay, bases will neutralize acids. Okay, and they will cause the displacement of ammonia from ammonium salts. So what that really means, if I have an ammonium salt, remember the polyatomic ion ammonium is the NH4 plus ion. So if I have that in solution and I mix that with a basic solution, I will get a reaction that forms the salt and also forms NH4OH. This sets up an equilibrium with ammonia and water. And that's something to know. This equilibrium lies to the NH3 side. So it is probably more accurate to write this as that. Okay. Okay. Let's just, last thing for the screencast, strong acids. There are 7 of them that you should know. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, and perchloric. You should all know that all of these fully ionize. Your strong bases are hydroxides of alkali metals, and heavy alkaline earth metals. That would be your calcium hydroxide, strontium hydroxide, and barium hydroxide. Okay. That ends that screencast. We'll pick up with, you almost thought you were done. Weak acids is basically everything else not on that list. Weak bases. This is important that you know that NH3, ammonia, is a weak base, and the amines are weak bases. For example, C2H5 and H2, that's an N, are weak bases. Now the screencast is done.